This is a short video about a couple examples of showing a function is continuous and differentiable and the relationship between those two concepts. So I think we may have looked at this function before. Look at this piecewise function that's f of x. It's x times sine of 1 over x as long as x is non-zero, and it'll be 0 when x is 0. So the first thing I claim is that this thing is continuous for all real numbers, x and r. And so maybe you remember this thing has some pretty crazy oscillation. I'm saying if we assign the value to be 0, then that makes this function continuous. And let's see, have I got a picture for you? Yeah, I do. All right, so if you check this out, there is this crazy function, and what I want you to notice is that as you get close to 0, right, it starts to oscillate super duper rapidly. So let's get back to this. How would you show this here? Well, if x is non-zero, then you're looking at this formula here, right? And in that case, x is continuous, and sine of 1 over x is continuous as long as x is non-zero. Therefore, that's the product of two continuous functions, which I know to be continuous. So what we need, the limit definition of continuity, is for showing that f is continuous when x is 0. So what would that proof look like? Well, we're going to utilize the fact that the absolute value of sine of 1 over x is always less than or equal to the absolute value of x for every real number x and r. And what we'll do is we'll kind of expand this like you would in college algebra, say. That's the same thing as this compound inequality. Minus absolute value of x is to the left, and then regular absolute value of x is to the right. And I know x sine of 1 over x is always between those two. Now what we'll do is we'll take the limit of all three sides here. Remember, if these inequalities hold for all x and r, then the same relationship should hold between the limits. And what do you notice the limits of the ends are? Those both go to 0 as x goes to 0. So therefore, I get that, in fact, the middle has to go to 0 as well. That was the squeeze theorem, or some books say that's the sandwich theorem. So we just proved that the limit as x goes to 0 of our function is 0, which happens to be what you get when you plug 0 in for x. In other words, you get the value f of 0. So this is continuity, right? Limit as x goes to 0 of your function ought to just be f of 0. So we've proved that it's continuous at 0. So at this point, you should be thinking, all right, maybe this function's not so bad. Maybe this function f of x is kind of nice. It's continuous. And so the next thing I want to tell you about is, in fact, it's differentiable for all non-zero x as well. And so when x is non-zero, well, then it's just this nice formula up here. And remember, those are pretty nice functions. Like I've got derivative rules that maybe I remember from calculus. And so like, how do you differentiate a polynomial like x? How do you differentiate a trig function like sine? I've got the chain rule, and I've got the product rule that tells me how to differentiate, well, a product. And so we'll use the product rule and the chain rule. So what you would get if you differentiated this is my f prime times g, and then I've got g prime times f. That's how I usually remember the product rule. And we'll actually do those derivatives in the next step. Remember, that turns into 1. And then here you need the chain rule. And so in that case, I see I made a typo. This should definitely be a cosine of 1 over x times minus 1 over x squared times x. I bet you I did that down below as well. And remember, this comes from the chain rule. In the next step, I want to simplify these two. That just gives me a minus x that I'll probably just put in front of that cosine. And so what's this look like? And again, you see this, change this to cosine and change this to cosine too. So that would be a good formula for what the derivative is as long as x is non-zero. The problem though, so I've got to undo these, is that f's not differentiable at x equals 0. And so this problem really emphasizes this relationship that being continuous is not enough to conclude that your function is differentiable also. So to show this, what we'll try to do is use the limit definition of the derivative. Remember, this is the limit definition of the derivative applied when my value c from that definition from earlier videos, say, is 0. So let's actually compute that. So like the formula for f of x is x sine of 1 over x, since x is non-zero as it's approaching 0. And so if I was to simplify this difference quotient, well, I don't need to write the zeros there. And the next thing I see is that these x's should cancel. So the difference quotient here just simplifies to sine of 1 over x. Well, what does that do as x goes to 0? Well, that goes nuts, right? That oscillates up and down infinitely often, so that limit does not exist. So what we just showed is that the limit here of this difference quotient, which ought to be what the derivative is, does not exist. So that shows our function, again, is not differentiable at x equals 0. All right, let's change our function a little bit. Let's change it up, and all I did was I put a higher power x in front of sine of 1 over x. I claim that this function is much nicer. I claim that all the following hold are all what we just showed hold, but in fact f's differentiable for every real number, in particular at x equals 0. And so in this case, you get a similar idea for what f prime should be. And again, I think I made a typo. I think that should be a cosine of 1 over x right there. Just by doing, your product rule and your chain rule kind of stuff like that. But let me show you what this higher power of x does. That helps us make sure that f's differentiable at x equals 0 as well. And so let's take a look at that. So to see f's differentiable at x equals 0, we'll again look at the same limit definition of what the derivative should be. And again, if this limit exists, whatever that number is f prime of 0. If it doesn't exist, then I'm not differentiable at that point. And by me, I mean f, of course. So if I was to substitute f of x as this new formula, x squared sine of 1 over x, this new function I'm considering. And now in this case, what this difference quotient simplifies to is really x times sine of 1 over x. And why is that cool? Because I know from above, what we started this video off with, is that goes to 0. So why is that great? Well, I got that's this limit, it's a number. So that means f prime exists. So f prime of 0 exists, and we can conclude f prime of 0 should just be 0. So I made a recap, and again, another typo here. F prime of x is equal to, here was my formula as long as x is not equal to 0, which comes from using my derivative rules on the actual formula given here when x is non-zero. But then what we just also established is that when x equals 0, we can say that f prime should be 0. So that would be, so the derivative is again a piecewise function. And something else to notice too, if you're looking at the derivative itself, right? Like I see that as x goes to 0 in this formula here, well that cosine piece is gonna go nuts, right? So this would end up going away. Cosine 1 over x is a problem. So I see that f prime exists, it's a good function, whatever, but it's not continuous either. So that's also a good example. Just because you have a derivative, that doesn't mean the derivative is nice.